this so you guys can know what to do with thermo. If you're not doing the thermochemistry and you're just doing the organic exam, keep on working for the rest of the period. Tomorrow I'll have you guys go and you guys will get some organic ideas. Make sure you're using those highlighters because it's really useful to know what you know and don't know. And then anything you're writing down now, you now have that red pen so you can annotate that in red pen so that way you know what is kind of the feedback that I gave you and what needs to really, really work. So here are our answers. I will be following the same color coding as I normally do. So achieved is going to be in red. The merit will be in blue. I might actually choose a different blue because that's quite a dark color. Huh? For yellow is what's in your brain, blue is what you needed to use your notes for, and green is what you needed to help with a friend. And then I've given you a red pen so you can mark on it as I go through the answers. And then excellence will be in green. Oh, I don't like that green. Let me use a different color green for that. Another picky. Just want it to be nice and easy to see on the paper. There you go. The other thing I'm going to do is I'm going to show you guys how to process the question. So when we're thinking about that, I will do that in orange. So orange is just to show you how I process what the question is asking me for. It's really useful to actually annotate your questions as you're going through them to help you kind of figure out what you are doing. Keep in mind you're going to be obviously given a periodic table for this. I'm actually going to go grab myself one. To help us answer these questions. All right, so this is the 2017 mock that we gave our students. So very strange setup, very different from what you guys are used to. So it's really useful to see this in a different format. What they have done is they've given you 3 different elements, and they've given you both the element and the ion for it. And they've given you the atomic radius and the ionic radius. So it's a nice big table. You need to be really careful then what you're pulling for that compare and contrast. And also keeping in mind what that question is asking for. It's also very strange in the fact that they want you to do the electron configuration and the trends in the same question. Normally, what we do is we have the electron configuration as its own separate kind of achieved, maybe merit level, and then you have your explanations. So keep that in mind. This is a very strangely structured question. Very unlikely you'll get that on the exam, but good for you to see it in different format. So the first thing they want you to do is electron configurations, and they want you to choose, I think that's scandium and copper, and they want you to do the S, P, and D notations. Remember that whenever you see copper, copper is an exception to the rule. It's very likely they're going to give you exceptions, either with the transition metals or the incomplete kind of or full kind of D shell things. So keep in mind whenever you see those guys. And they want you to explain the trend of the atomic radius across period 4. So again, I'm underlining it to kind of pull out the key information. The first thing was just to do the electron configurations. Do you guys want me to write them down so you can check them? All right. So SC was 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d1. It's okay if you have these the other way around. They won't be that picky on it. Copper is an exception to the rule. Remember, you're going to have an incomplete 4s shell, so that way you can have a full 3d shell. It's basically going to be the exact same numbers except with that change. If you want to do the shorthand and do the elements, that is also fine. Just make sure you're grabbing the right noble element. Cool. So that's what you should have gotten. And then you're going to have to do that again in part 2. And I'll talk about that first achieve point when we get to that. All right, so with this question here, they want you to identify the trend growing across the period. So be really careful. When I look at the periodic table, we're talking about these two things that are in the same row number 4. So you're comparing against those two. For the achieved, you just need to state the trend of atomic radii. So what happens when I go to the right? Does it get bigger or smaller? You get a 50-50 chance of getting it right, so take a guess. Smaller. So as we go that way, it gets smaller. I'm going to be shorthanding it to save us time. That is going to be your... Ooh, I'm going to wait until the very end to tell you how the points break down. Are we good so far with that? So these are all kind of achieved level questions. The merit point then is being able to explain why. So thinking about the trend, we need to kind of keep in mind that there's several different layers that we need to be talking about. The first kind of thing that we need to think about is that we are adding electrons and we are adding protons. But the thing is, we are adding the electrons to the same energy level. And so since they are at the same energy level, it has the same shielding effect. Are we okay with that so far? So when I think about layering the answers, I could say as we're going across, we are increasing proton and we are increasing electron numbers. Are we good so far with that? If you want to use some linking words, you would then use things such as however or but. It's in the same shell. Do you guys know which shell number it is? Third shell. All right. So that's how I'd be linking it in, and then, but it's in the same shell. And since it's in the same shell, you have the same shielding effect. Are we good so far? So since it's in the same shell and it has the same shielding effect and we have increased proton numbers, you can start combining these two ideas together and stating, same shielding, more protons, smaller radius. Greater pull, therefore smaller radius. And you could also stick in some of those keywords. So even though we're increasing the number of electrons, since it is in the same shell level, that's not a problem. Are you okay with that so far?
Wait, could this one get to 8?
No. So the whole part A, let me look at part A. Yeah. This bit and this bit only go up to merit. But there's 2 merit points here. Cool. So this here is your first merit point. And I'll talk about what the achieved points are once we answer that second question because it talks about how you could have done that. Are we good so far with that? Is that easy peasy? All right. Next one here is the same factor, electron configurations. But in this case, you're using the beryllium atom and the beryllium ion. So again, we're being very mindful of what we are grabbing, which is these 2 numbers here. So if you want, you can circle them in different colors when you're doing it, so that way you know. All right, I'm comparing this one and this one for my first question, and then for the second question, I am comparing this one and this one. Doesn't hurt to annotate it because it helps you kind of keep everything clean and tidy. All right, so first thing I need to do is the electron configurations. These ones should be nice and easy to do. For beryllium, you should have had 1s2 and 2s2. For the beryllium ion, it's now a 2+, so I've lost 2 electrons. I've lost this whole shell, so I just have 1s2. Are we good so far with that? All right. Now that I have all the electron configurations, I can give you guys the first achieved point. You see how there is 1, 2, 3, 4 electron configurations? For the first achieved point, you needed 3 out of the 4 electron configurations for that achieved point. Cool. All right, second thing to think about is general statements for the achieved. So the thing that you have to notice is that looking at this, I see that beryllium has decreased in size dramatically with the beryllium ion, and that's because it's lost its outer shell. So for the way you can get the achieved point is beryllium is smaller because it has lost the shell. Remember, if you're gaining electrons, you're not gaining shells, so be really careful. This is very specific to positive ions. Does that make sense? All right, for the second achieved point, you either got its smaller trend as you go across, or you said that beryllium is smaller because it lost a shell. It's an or option. There was only one achieved point that was going to be offered for those, and that's your second one. So there's 2 achieved points in question A. Are we good so far? All right, next thing then is giving us our reasons. So why is it smaller? There's multiple things you need to be talking about beryllium. You would talk about how they're both the same species because they have the same, they're still both beryllium, so they have the same protons. But you would be talking about how beryllium 2+ is smaller because it's lost the shell, and there's more positive charge, and so it's going to pull tighter. We good for that? This one should hopefully be a relatively easy justification. But make sure you have both of them. You need to talk about lost shell and the ratio of charge to get that merit point. So this is your second merit point here. Unfortunately, there was no excellence point for this question. I have seen in other exams, though, if you get both of these at the merit level, they give an excellence point. But in this case, they didn't. So kind of strange in that sense. Ooh, I don't know if I'm going to have time to finish all of this. That's okay. Good note for next time. All right. This next question here was on electron negativity and ionization energy across period 3. So once again, we're talking about the trend going this way. First thing they want you to do is talk about ionization energy and electron negativity. Then they want you to explain the trend. And then across the period and across the period. Oh, and then elaborate on that trend. Actually, to save us some time, I might put the marking schedule up on the board so you guys can see the difference. And that way you guys can still get the full answer. All right. So what we're looking at for the ionization energy and electron negativity for the achieved point, your third achieved point is, did you define one of those terms correctly? So be mindful, ionization energy is talking about the energy required to remove the electron from the outer shell in the gas state, whereas electron negativity is talking about that force of attraction between that nucleus and covalent bonded electrons. Both of them will increase as we go across the periodic table. So definition for one is the achieved. Definition for both, surprisingly, was a merit point. So that's your third merit point there. Very odd. Cool. Then what they wanted you to do is talk about the pattern. And again, once you're going to use a similar kind of structure for all of your pattern justifications. For example, you'd be talking about how across the period, there's no additional shielding because everyone gets added to the same shell. Make sure you have that whenever you're talking about across the period. You would then talk about, though, however, proton number increases. As my proton number increases, I have a more effective nuclear charge, nuclear attraction, nuclear pull, and all those things pull those electrons closer. In this case, what you would be talking about, the pull, that attraction, that's the electron negativity, and then the energy required to remove it, that's the ionization energy. So keep in mind when you're looking at that sort of stuff. Merit point, this one is merit point number 4. You explain the general trend, and in this case, you were only talking about electrons being added to the same level, or you're talking about there's no change in shielding effect. A merit level student only talks about one of those two things. An excellence level student will talk about both. So do kind of keep that in mind. So here's the excellence, a full justification, and you're using both proton number and shielding in your justification. Are we clear with that so far? All right, last one here might have tricked you guys. Draw your Lewis structure diagrams. I know it asks for a shape. It is very, very unlikely we will ever ask you to draw a shape. So I would discredit that as a question. It wouldn't be likely. But you do need to name the diagram, so do kind of keep that in mind. 2 Lewis structures to be correct, a Lewis structure and, either 2 of your Lewis structures are correct, or you only got 1 Lewis structure correct, but you also got its name right. And then basically this one only went up to the merit point. You got the Lewis structure and the name correct. They did include diagrams as points, but I wouldn't expect them to use diagrams or shapes to be complicated. All right, this one here, I don't know if this one threw you guys off about solubility. The answer was the CF4. Looking at this, it's a charged ion, so you'd think that would also be soluble. So I think there was leeway to give you some points for that. I think the key was that this is an ion, whereas this is a molecule, and that's why that one was the right answer, along with it not being, along with it being a polar molecule. It is not symmetrical because of those lone pairs of electrons and its seesaw shape. So here it just points on describing it, and then the next thing is talking about dipoles, don't cancel out, it's a polar molecule, and then how it's going to be attracted to the water molecule. So another cheat point, what are we at? 1, 2, 3, that's 4. This is the 5th cheat point. Either you chose the compound and the molecule correctly with polarity, or you described the shape correctly. The merit point was 2 explanations explaining polarity, but you might have missed, for example, electron negativity. Make sure you layer your polarity answers. Use electron negativity to justify why you have a polar bond. Well explain link information, and then for the excellence, discuss as well, and then explaining why it's soluble in water. So again, this one was a very strange question. Usually they don't kind of give you 2 things that could be soluble. I think in this case, it is a non-polar molecule by the looks of it, but it does have a charge on there, and I'm not sure how that charge is affecting water solubility. Again, this is kind of a weird curveball question. I wouldn't expect you to do this on the exam. Okay? So, can you guys please take a picture of the CPR quiz so I can collect that? Please hand in your markers and put in the pen. The red pen should go into that bag now. If you have any other work that you have finished in today's period, I will collect it up as well. Because like I said, I'm collecting everything as evidence. So, stretch your legs, drop things in my box, put my markers back.
This is the only thing I have to finish today.
So tomorrow what I'm going to do is I'm going to do the second question of the mock, but with you hand it in, I can give you some feedback. Yeah.
This one, I haven't done it. Do you want it?
No, I only want it once it's done.